My name is Ben Hawkes, and I'm a member of Project Zero. This talk is about software exploitation, what makes software exploitation hard, and why does it even matter? About 18 months ago, a group of security engineers at Google formed Project Zero with the stated mission to make zero-day hard, to make software exploitation using zero-day vulnerabilities harder than it is today. And behind that sort of encapsulates the idea that we think that the cost of an exploit is not in balance with the capabilities that an attacker gains from using that exploit. And also, we knew that there was a private market for exploit purchase and sale, a global market for exploit purchases, and the exploits were being used to harm our users and to harm companies like Google. And we thought, as security engineers, that we could work on this problem. Here's a concrete example, $130,000. This was the purchase price recently for what we might think of as the canonical exploit chain of recent years, at least, which is an Adobe Flash exploit, zero-day exploit, combined with a Windows kernel exploit. It's $40,000 for a Flash exploit and about $90,000 for a Windows kernel exploit. And at first glance, you might look at that number and think that's a lot of money. If you compare the cost of setting up a phishing operation or something like this, this is much more expensive. But then if you think about what this exploit is, it's a full system compromise on hundreds of millions of machines, just by having a user visit a URL you control, or if you have network access and the ability to inject into network traffic, not even that. So all of the classical targeted attacks that we've heard about, system administrators being compromised and network access being stolen, diplomats losing documents, company executives losing emails, cryptographic key material being stolen, backdoors being inserted, all of this is open to you by this exploits capability. So in practice, we think exploits are too cheap and too numerous. So this talk is, in essence, about our technical strategy to try to address this problem. There are other non-technical facets about how you might approach this, policy issues, outreach, education, but today I'm focusing on our technical strategy. I want to sort of explain the observations and principles behind our technical strategy, why we think it's effective, and then obviously get feedback from you all about whether you agree with that assessment and ideas of other sort of technical facets that we could introduce into our work on this problem. In essence, our answer to the question, what makes software exploitation hard, is twofold. It's strategically targeted vulnerability research and incrementally increasing the state of the art of exploit mitigations. But in essence, behind that is the idea that Project Zero is an attack research team in the same mold that a private attacker and a private actor might want to set up, except we do our work transparently in the public for defensive purposes. In 18 months, we've reported 600 vulnerabilities, most of these in non-Google software. So importantly, our scope is beyond just what Google is producing as software. We look at holistically all the types of software that are used in the ecosystem of our users. 600 vulnerabilities in about 18 months. We have a blog that focuses heavily on technical reports about how you discover vulnerabilities, exploitation, how exploitation actually happens, and mitigation design and how we can break mitigations. There's a new blog post comes out about every second week. And we've also been involved in shipping some exploit mitigations. I think of Chrome, Linux, Flash, Windows, Android, all ship mitigations that either influenced by our work or directly designed by our team. As a start, I'd love to do more of this final point. We'll address that shortly. But here's another number, 26. So 26 is the number of cases of exploits discovered in the wild in 2015 that affected the set of software targets that we're monitoring. This includes Internet Explorer, the Windows kernel, Adobe Flash, Microsoft Office. 26 cases of discovered zero-day exploits in the wild. And at first glance, again, you would look at that number, and we're very used to in the security community hearing very high numbers of thousands of attacks per day against systems and so on. And this is relatively a small number. But we have to decompress that and look at what's behind it. This number, 26, represents the failure case for the attacker. It's where something has gone wrong, some technical process, some operational security procedure has gone wrong, or the attacker just gets very unlucky in order to allow the security community to detect and discover these instances of zero-day attacks. But there's an unknown here, and the unknown is the ratio of discovery to non-discovery. We don't know the rates that zero-day exploits are being used in the wild for which we're not seeing, for which we're not discovering. So we need to be very careful about looking at this number, this failure case, and taking it too far, taking too much insight from just this number alone. And the idea behind this is something that is, I think, very central to my approach to security, which is this idea that it's the attacker's job to deprive us of the data that we need to make optimal decisions about defense. This is, I think, a significant mindset, and it's stating the obvious, of course. Security is unique in the sense that we have an adversary, and as engineers, our desire to be data-driven in all things, it's very strong. It's natural, in fact, but security is a little bit different in the sense that in many cases, not all cases, but in many cases, just taking the data alone at face value will lead to suboptimal decision-making in security. So we try to think about a little bit deeper what is going on behind the scenes, what is the model that we can build about attacker behavior. One approach is to start to imagine yourself as an individual attack researcher. On a day-to-day basis, Project Zero is performing this work, and we know also the individual anxieties, the things that a researcher worries about on the attack research side. It's questions like this. Will I be able to find a good vulnerability? We know now that not all vulnerabilities are equal. Some are more useful than others. What are the chances that this particular bug I've just found will be fixed? What might be discovered by the vendor itself or an open source project. It might be discovered by another defensive security researcher. That's very disruptive to me as an attacker if I want to use this bug as an exploit. And how long will it take me to write an exploit? We know that attackers are also resource constrained, and that even though theoretically a bug might be exploitable, there are prioritizations that have to take place. And how can I make this exploit reliable? Reliability is something that I think defense understands very poorly in the context of exploitation. When you're attempting to use an exploit in the wild in an operation, if the exploit fails, this is a very costly thing to occur. So we need to, as attackers, make those exploits reliable. Now, at Project Zero, we think about these questions, and we think about how best to approach each of these in a way to heighten the concern of the attack researcher, the anxiety of the attack researcher. So I want to dive into our technical strategy a little bit. There's two sides, the vulnerability research and there's the exploit mitigation side. And I'll start with our vulnerability research. And our strategy really is based around one idea, which is what we call contention. And contention is the occurrence of multiple researchers running into the same output as a researcher. Bug collision, or research rediscovery, in essence. Our strategy is built around trying to increase the rate of bug collision between ourselves and attack researchers in the private market. We do this in sort of two main threads, not exclusively, but primarily these are our two approaches, the pincer strategy that we use. The first is to eliminate low-hanging fruit, to use Google's immense machine resources and our incredible access to corpus data, file format data from our web crawler and other sources, to build some of the world's best fuzzers. We know historically that fuzzing is a method that a subset of attackers are willing to use. Perhaps they're not the most advanced attackers, but there are attackers out there who are willing to use fuzzing as a methodology to discover bugs that are then exploited. And we think that's just unacceptable. It's too easy, it's too cheap, and we believe that we can actually substantially affect the ability of attackers to use fuzzing as a viable research methodology. On the other side, and there I would say that the contention comes from a shared methodology, a shared approach. There isn't such a wide variety of fuzzing techniques at this current moment that different fuzzers are always going to find different sets of bugs. There's going to be some level of overlap in the output of independently written fuzzers. The other approach is the last step of the bug chain. And here, what I want to emphasize is that a modern exploit is not a single shot vulnerability anymore. They tend to be a chain of vulnerabilities that add up to a full system compromise. A classic example of this is when you attack a browser, you need a renderer process bug and you need a sandbox escape. Then you may even also need a kernel bug to get administrator access. So the observation here is that the attacker requires the full chain, the complete chain, in order to have a complete capability. And along the way in that chain, there are some parts, some links of the chain that are more fragile than others, that are perhaps constrained attack surfaces or that are less densely buggy in some sense. And this is where we've tried to focus much of our effort. The prime example would be a sandbox escape or a kernel privilege escalation bug. And here we're really willing to use any methodology possible, a mix of automated methodologies and manual approaches, manual analysis. But the question still remains, how on earth do we know what to look at? There's such a wide variety of software targets out there in the world that are potentially under attack. We are very limited in our individual resources. Our team size is around 10 security researchers. So we need to prioritize our own target selection. And again, this comes back to the idea that we don't have perfect insight into the target selection of attackers. They don't share their lists of exploits that they have stored up. They don't share the list of software targets that they're willing to purchase exploits against. So we need to model this again. And for us, it's a mix of different sources of information. Firstly, we look at that number, 26, the observed attacks, and try and gain some insight from that. But as I mentioned, this is a little risky when you're studying the failure case of the attacker. If you draw too much into that, you may run the risk of drawing false conclusions. So we also try to gain other insights about what the attackers are going after. So a mix of external feedback from participants within the private market, either directly through our relationships with them or through other means where public information becomes public about that world, which happens from time to time. And the final, I think perhaps the most useful that I find, is our own internal deduction. The premise of our team is that we hire some of the top vulnerability researchers in the world. We want to use their expertise and their experience to predict, to have predictive value about what they think will be the next big thing. More often than not, I believe they are right on the money. So in practice, what does that mean? We're focusing heavily on endpoint attacks against ubiquitous software systems. So mobile is a big thing. We work on both Android and iOS. Desktop operating systems, the major kernels are a big part of what we work on. Almost every browser is on our radar, and document readers, and recently also antivirus, endpoint security systems. But vulnerability research is only one side of the coin. We have a pipeline of sorts where we find vulnerabilities. For some set of those vulnerabilities, we write exploits. And then from those exploits, we gain insight about the state of the art of exploit mitigations. And this is an area where we think that our practical insights about the realities of exploitation can lead to better exploit mitigations. There's kind of two sides to that. In the process of writing an exploit, we have to bypass exploit mitigations that are already shipped to users. So in essence, we can find those edge cases, find the areas where an implementation is not correct in relationship to its design, or that the design is not sufficient in all cases. And then on the other hand, we can start to plan or suggest new ideas for exploit mitigations. So using our insight about our own exploits, we have a sense of where in the exploit is their fragility. Where did we get a little bit lucky, in essence? Where might we incur a lot more time or effort if we had a new mitigation idea? And then we share that with the broader software development community and this broader security community. In that sense, I see ourselves as advocates for good exploit mitigation design. There's a lot of bad exploit mitigation design ideas out there as well. But I've been talking about exploit mitigations without actually really defining what I mean. And this is something that I think in the past, as an attack research community, we've been quite bad at, is just talking in generalities and not in specificity. So this is one approach, or one sort of, what we call it a taxonomy. It's a vocabulary, if you will, about how to talk about mitigations. It's not the perfect taxonomy. It's not the only one, certainly. It is sufficient as a starting point. So to run through some of these, a strong mitigation. These are ideas like recently Microsoft in their Edge browser has shipped a new allocated type called memgc, and this may well be considered a strong mitigation now. It's early days yet. It might end the bug class of use after freeze in Microsoft Edge, which would be a really amazing accomplishment of Microsoft's. Another example you might consider /GS or DEP, stack cookies, making stack buffer overflows more or less unexploitable, or perhaps other forms of compiler technology, CFI, CFG. Now, weak mitigations is a little bit more on the tactical level. So we observed often that there's commonalities between a sequence of different exploits where they're relying on the same ideas. And a recent example of this is Project Zero's work with Adobe. We worked with Adobe to partition out a certain object type called the vector of viewants, which we had seen in exploits time and time again over the last 2-3 years. And by partitioning out that particular object type, it forced attackers to find different objects to go after. Eventually, this leads to a more generalized approach and a generalized solution. When saying that something is a weak mitigation, it doesn't necessarily mean it's worse than a strong mitigation. It's just the observation that the properties that are given by the mitigation is unlikely to stop the exploit from occurring. It's about the overall cost, the investment, the time investment going into the exploit. There's a couple of other types of exploit mitigations that I'll just briefly discuss. And they're on the verge. Some people wouldn't consider these exploit mitigations. Personally, I do. And there are two types. Attack surface reduction. So an example that we're working on at the moment with Chrome is, as we mentioned, the canonical exploit chain is a Flash exploit combined with a kernel exploit. Now, the problem, in essence, is that Flash has access to the kernel. Does it need it? It turns out perhaps it doesn't. We're working on the project to remove access to Win32k from the Flash plugin process to effectively remove the kernel attack surface from the purview of Flash. Other examples are font transcoders, shader transcoders, the types of ideas that we've had in browser security in the past. And the final idea is perhaps the rarest type of mitigation, chain extension. As I mentioned, exploit mitigations are chains. Sorry, exploits are chains, and that the longer the chain is, it means effectively that a new bug has to be discovered. The chances to introduce a chain extension are actually quite rare. You can think of perhaps something like ASLR, where you now need an information leak bug, or introducing a sandbox, or virtualization ideas, where you need a VM escape. These are the types of ideas we would consider under chain extension. So to wrap things up just quickly, here's a quick example of one of the projects we've been working on. I've mentioned it, Flash. We've reported about 180 vulnerabilities in 18 months, and we've worked with Adobe very closely, and Adobe have been working very hard on exploit mitigation improvements. The observed price increase for an exploit, based on just the public data, not with any sort of private market insight, was 60% in 18 months. I'd like that to be higher. The reality after some of these mitigation improvements, we may well see an increase in that price over time. Definitely on the ground as individual researchers within our team, we have noticed the difficulty in performing exploitation work against Flash in the last 18 months. So what makes software exploitation hard? For us, it's the combination of vulnerability research and exploit mitigation. One without the other is not quite as effective. If you just perform vulnerability research, you're ceding an advantage to attackers when they do eventually find a bug. You're letting them build reliable, reusable exploits for a very cheap investment. On the other hand, if you only perform exploit mitigation, we know that most mitigations have documented edge cases. If you have a very densely buggy attack surface, then it's easier to find edge case bugs which aren't covered by your mitigation approaches. So we need to think of exploits as chains. There's two approaches. You make each link harder to achieve, or you extend the chain. Thank you.